Hello everybody and welcome to our video today where we are talking about organic chemistry, chapter 7, aldehydes and ketones, part 2, which talks about enolates. So let's get started. The first thing that's covered in this chapter is the acidity of the alpha hydrogen. So the acidity increases the more it is easily removable, okay? And the next point here is that the alpha hydrogen is attached to the alpha carbon, and the alpha carbon is adjacent to the carbonyl carbon. So we'll say that again. If we're looking at this image right here, right, we have the carbonyl carbon, which is here. The alpha carbon is attached to this carbonyl carbon right here. So the alpha carbon is here, which means the alpha hydrogen is the one that's attached to this alpha carbon, which would be this hydrogen right here. Okay, so this is our alpha hydrogen, and it has an increased acidity because it's easily removed, right? Compared to, some other hydrogens, this one will be easily removed. And this is the case because as we go down here and we're looking at increased acidity, means that there's an increase in electronegativity, right? There's an increase in resonance or an increase in induction. So all of those things cause an atom to be more acidic, okay? So this right here is increased acidity because it's easily removed, and it's easily removed because of the induction effect of this oxygen right here. So this oxygen being here pulls the electron density up to this area, right? Which means this bond is weak, which means it's easily removed because of induction, because of this oxygen being so electronegative. Okay, so that's just how we can look at that. The other thing is that the alpha hydrogen in ketones is less acidic because it has electron donating properties of its alkyl group, okay? So again, we'll look down here. Electron donating groups decrease acidity because they destabilize the molecule, and electron withdrawing groups increase the acidity because they stabilize the negative charge. So this is all related to, what else is in the molecule. So like we said, for something to be more acidic, it will be easily removed. So electron withdrawing groups increase the acidity because when that electron is taken away, that charge is able to be compensated throughout the rest of the molecule. Whereas with electron donating groups, they're going to destabilize the molecule because you're adding something to that molecule, right? And it's getting kind of thrown off. You're adding another atom here, another charge. Like, what are we doing? So that is why this would decrease acidity, because it is destabilizing the molecule. Whereas with the electron withdrawing groups, if you're taking away this electron, you're allowing the molecule to compensate for that charge, and that would increase the acidity. So all of that is important going into our next, section of the chapter, and really all of organic chemistry. These points here in blue, I would definitely recommend studying, knowing, and understanding. But next, let's get into the enolate chemistry side of things. So we have enolate chemistry. So we have keto and enols, okay? So the keto form of this molecule is carbon, carbonyl carbon, carbon, with the double bond to the oxygen, right? So this is the keto form. And then we also can have an enol form of this, right? And so that means that we're having, instead of having a double bond to the oxygen, we're having a double bond to this carbon, and the hydrogen is up here creating a hydroxyl group. So that's kind of the two forms that this can take. And these are tautomers because they're isomers, right, by moving the hydrogen bond. So the reason these things are isomers is just by moving the hydrogen placement, right? Before it was here, and in this one it's up here. So the kinetic enolate form, which we're going to look at down here, is faster, irreversible, and less stable, while the thermodynamic enolate form is slower, reversible, and more stable. So what that means is if we're looking at this molecule here, right, we have this hydrogen. We have this hydrogen right here. And we are going to, it's going to be removed. And when it's removed, you're either going to have this version or this version. This is the thermodynamic version, okay, which means it is more stable because that double bond was formed here. But it does take a minute because initially if you're removing this hydrogen, the charge would be here, right? And then it's going to take a minute to actually form the double bond over here. In this form, this is the kinetic form. This is when the double bond is over here, but this molecule is less stable. So it occurred faster, right? Because you just took this hydrogen here, so those electrons just went here, but this is less stable. So that's just, knowing the difference between the thermodynamic enolates and the kinetic version of that enolate, okay? So aldol condensation. An aldol is an aldehyde plus an alcohol, okay? So there's two parts to this reaction. We have aldol addition and aldol condensation. And once both of those steps are performed, you will have a double bonded, a C double bond to a C, okay? So I'm just going to move this down there so you guys can see. So the first thing that's going to happen is we have this molecule, right? And we have OH in the solution. The OH minus is going to be is going to take away this hydrogen, right? So now you take this hydrogen, and what happens is the bonds in this the electrons in this bond are going to come back to this carbon, and then that's going to force the bond between the carbonyl carbon and the oxygen to break, and it'll be up there, which is how we get to our second stage right here. So that's why we have a negative bond on that oxygen, okay? What's going to happen is this is going to reform. However, that's going to cause the carbonyl carbon to break one of its bonds, right? Because carbon can only have 4 bonds. So when this bond is remade, these electrons in this bond are going to be attracted to this partially positive carbonyl carbon on this molecule, which again is going to cause this bond to break and leave us with another negative charge on our oxygen. Then this is going to have to reform, and you are going to get an aldol. So once that reforms, it's going to become an aldol. And I know you can't necessarily see all of the steps in between. So if you want to see those steps, you could look them up. But this is the most important part. Is just after this, you're going to get the aldol. Okay. Next, we're going to take this molecule, and we have to do the aldol condensation. And condensation means that H2O is going to be produced. So we have our H2O being produced here. Okay. And how this happens is the OH here, okay, is going to take this hydrogen off. So when that hydrogen is gone, the electrons in this red bond right here, they are going to be pulled towards this area of the molecule right here where the water just left. And water is a good leaving group, right? So let's just back up a second. We have OH and hydrogen. This hydrogen is going to come here, creating water. Water is a good leaving group. When this water leaves, it's going to create a charge right here, which is going to cause the electrons in this bond to form another bond right here, which is how we're getting our double bond right here, plus H2O. So this is the full aldol condensation. Just knowing the steps and where the molecules move and what charges are created is, probably important. But yes, just know that aldol condensation has 2 parts, aldol addition plus the aldol condensation, both of which will create a carbon to carbon double bond plus the production of water.